In this lecture, we are going to see the concept of AVL trees. Basically, these AVL trees are the extension of the binary search trees. We have seen in the previous videos or previous lectures that a tree is a generic structure. On that generic structure, if you provide the condition of having maximum of 2 children, then it is said to be binary tree. On binary tree, if you can put a condition of arranging the elements that for every node in the tree, the left subtree must be, the elements of the left subtree must be lower than the corresponding root node, and the elements at the right subtree should be the greater will be the greater than the element of the root node. So this is the uh, arrangement condition that was made on the binary tree. Thereby, it becomes the binary search tree. But in the last lecture, we have seen the main disadvantage of the binary search tree. Even though the binary search tree searching will be of log n, this will be satisfied or this will be guaranteed only when the elements or the height of the tree is balanced. If the height of the tree is skewed either at the left side or right side of the structure, then we cannot achieve the property of searching an element in the log n complexity. That is the reason this AVL tree is an idea of adding one more constraint on the binary search tree, that is called height balancing. We are going to in this particular tree, especially the height balance was proposed especially to maintain searching complexity as log n. This is what the advantage of the AVL tree while compared to the binary search tree. However, we need to perform the height adjustment for every insertion and deletion operation that will perform on the AVL trees. That means whatever the code that is used in the binary search tree, the same code will be used. However, for every operation, that is every insertion and deletion operation in the binary search tree, we are supposed to take care of the height adjustment constraint or height constraint of every node in the AVL tree. In order to perform this height adjustment, some specific operations such as rotation operations will be performed in the AVL trees. So binary search tree plus height condition is equal to AVL tree. Since the height condition is added, so few more functions will be coming into the picture in the AVL trees. So in this lecture, we will mainly focus on the insertion operation in the AVL trees. That means how to insert an element into the AVL trees. After insertion, what are the conditions need to be identified or checked, and based upon the conditions or based upon the structure of the tree after insertion of an element, what are the different operations that need to be performed in order to achieve the height balancing property. So let us start now. So the AVL tree is a self-balancing binary search tree in which the height of the two subtrees of a node may differ by at most 1. That means we can say height of the left subtree minus height of the right subtree should be less than or equal to 1. Because of this property, AVL tree is known as height balanced tree. In any examination, if you find the word called height balanced tree, then you are supposed to assume it as a AVL tree. Here, the key advantage of using AVL tree is it takes order of log n time to perform search, where n is the number of elements in the binary search tree or AVL tree. Insertion and deletion operation in average case as well as the worst case, the searching complexity will always be guaranteed as order of log n, where in case of binary search tree, only in the average and best cases only, the time complexity will be order of log n. In the worst case, that means if the tree is skewed either at the left side or right side, then this complexity cannot be achieved. The structure of an AVL tree is same as the binary search tree, but with a little difference. What is the difference? In this structure or in its structure, it stores an additional variable called balance factor. That means for the binary search tree structure, that what we develop using C program or C++, we have seen that struct node, in that we have seen struct node star left, struct node star right for indicating the left and right childs, and integer element, which is integer data, that is the value of the node. In addition to these three variables that we mention or that will declare in the structure of the node of a binary search tree, in addition to this, we'll add one more variable called height. So that means int height is one more variable that will add to the structure of the binary search tree node. So thereby it will become the AVL tree node. The balance factor of a node is calculated by subtracting the height of its subtree, right subtree, from the height of its left subtree. So the balance factor means, in our terminology, in the programming terminology, it is height. Height is equal to, that is height of the particular node is equal to height of the left subtree minus height of the right subtree. So if the left subtree is null and right subtree is null, then height is equal to null. Height is equal to 0, we can say. Or we may also initialize the height as -1. If any new node is added, -1 plus 1, the height will become 0. Like that also the program can be done. Here, the always we need to consider that a modulo or mod operation. Here, mod operation means is not percentile operation. It is a general mod, that means which indicates the plus or minus. So always this height is equal to, within mod, height of left subtree minus height of right subtree. Sometimes the right subtree may present or may not present. So the reason in such a case is if the right subtree is not present or left subtree is not present, then its value, that height value left subtree will become 0 and minus height of the right subtree. If right subtree present and if its height is 1, then 0 minus 1 will become -1. But we should round it to, we should figure it to a positive value. That is the reason I am going to add it as a modulo or mod operation. So within mod operation, we are supposed to mention this so that it will become plus or minus. That means mod means plus or minus. If there is a negative value inside the mod, then it will become positive. So that like that. So a binary search tree in which every node has the balancing factor -1, 0 or 1 is said to be the height balanced. The node with any other balance factor is considered to be unbalanced and requires rebalancing. That means for every insertion operation, once the insertion operation is done, the height value will be adjusted. The height value will be adjusted by considering the height of the left subtree and height of the right subtree plus 1. So since one more element was added, so we are going to add plus 1. In binary search tree operations, we have seen the height calculation. Height is always calculated as the height of the left subtree plus height of the right subtree plus 1. Sorry, height of the maximum of height of the left subtree, comma height of the right subtree plus 1. This is what the height of a binary search tree will be calculated. The same operation will use here also. If the balance factor of a node is 1, then it means that the left subtree of the tree is one level higher than the right subtree, thus the tree is a left heavy tree. If the balance factor of a node is 0, then it means that the height of the left subtree is equal to the height of the right subtree. If the balance factor of a node is -1, then it means that the left subtree of a node of the tree is level lower than the right subtree, such that the tree is right heavy. That means it is the terminology they have used for indicating whether there is a heaviness at the left side or right side are equally balanced. So this is what the terminology used. Here we need to focus on in the case of binary search tree, we need to focus on the height factor and also the adjustment factor, and also we need to look at whether the left subtree is heavy or right subtree is heavy. So with this, I would like to move on to the, instead of this presentation, I would like to move on to my lecture notes. So I will explain from that lecture notes. Anyhow, this lecture notes you can find in the link given, and also I have posted it on the Google Classroom. So you may also download that and you can view it parallelly. So here, this is the AVL tree. So AVL tree is the binary search tree with a balancing condition, so that it ensures that the depth of the tree is always order of log n. So thereby the search complexity in the best, worst and average case will guarantee the order of log n. The AVL tree is identical to the binary search tree, except for every node in the tree, the height of the left and right subtree can differ by at most 1. The balancing factor will be like this. As I told, it should be in mod. Height of left subtree minus height of right subtree is less than or equal to 1. In some textbooks, you will find less than 2. So less than 2 or less than or equal to 1, which is one and the same. When we do insertion, we need to update all the balancing information from the node on the path back to the root. That means if a node is inserted at the either the left subtree or in the right subtree, the balancing must be done. That means the height adjustments or height calculations must be done from the inserting node in the path towards the root. So it can be done by simple modification known as rotation. This is a very important concept in the AVL tree. The entire AVL tree is depending upon this factor, which is called rotation. So how this rotation operation need to be performed? Let us call the node that must be rebalanced is alpha. That means there exists the height imbalance at a node called alpha. The height imbalance might occur in 4 cases. So as this rotation operation is the key operation in the AVL trees, I recommend you to focus currently on this lecture. The reason is this is a very important topic that need to be understand in the AVL tree in order to write a code or develop your own logic for any question asked. So let us call the node that must be rebalanced. That means the rebalancing is required when there exists the height imbalance. Assume that alpha is a node which is having the height imbalance. So the height imbalance might occur in the 4 cases. The first case, these are the 4 cases you will come across whenever you insert an element into the AVL tree, and there may be a imbalance in the at the node level. So the imbalance means for example, alpha is a node where the imbalance occurred. That means that alpha's left subtree height minus alpha's right subtree height is greater than 1. That means it may be 2 or 3 or 4 or something. So in such a cases, you will get this particular imbalance. So this imbalance will occur in the following 4 cases. The insertion into the left subtree of left child of alpha. This is the case 1. That means the imbalance may occur because of the insertion of the node into the left subtree of left child of alpha. That is case 1. Second case, an insertion into the right subtree of the left child of alpha, because the insertion operation, while performing the insertion operation, always will compare with the root node. The inserting node will be compared with the root node. If the inserting node is less than the root value, then we'll move into the left direction, that is left subtree. If it is greater than the root value, then we'll move into the right subtree. Whenever it is moved into the right subtree, again the next node will be verified with the inserting node value. So if the inserting node value is less than the right subtree's first node, then we'll go into the left subtree of the that corresponding parent. Otherwise, we will go into the right subtree. So this is the way how the adjustment will, how the insertion will be taken place. During this insertion process, if the insertion is happened at the left subtree of the left child of alpha and alpha faced imbalance, then how the rotation has to be performed. So that is the case one. And second case, an insertion into the right subtree of the left child of alpha. That means the insertion is made into the right subtree of the left child of alpha. And insertion into the third case is an insertion into the left subtree of right child of alpha, then alpha faced imbalance. An insertion into the right subtree of right child of alpha. These are the four cases that will come across while we go for insertion into the AVL tree. The case one is an insertion into the left subtree of left child of alpha. You look at here the case one. Here 3, 2, 1. So 2 is an element which is less than 3. So that reason it was placed at the left hand side of 3. And 1 is an element which is less than 3 and also less than 2. So that reason it was placed at the left side of the 2. So assume that this is the, if you consider normally, this is a binary search tree. We can say this is an arrangement of binary search tree. But according to the AVL tree, we need to check the height balancing property. For example, if there exists only node 3, then its height is said to be -1. Then if 2 is inserted, then 2's height will become 0 or -1 or 0 -1. Then the 3's uh, 3 height will become the height becomes the left subtree height minus right subtree height. So then by what will become 3 height will become 1. Then 1 will be inserted in the 1 will be inserted into this tree. In such a cases, 1 height will become 0 because there is no left subtree and right subtree, and 2 height will become 1 and 3 height becomes 2. Thereby here this is the 3 is equal to alpha in our case, because the rebalance occurred or the imbalance occurred at the alpha. The imbalance was occurred at 3 since the height of the left subtree is 2 and right subtree is 0. 2 minus 0 is 2, but the height of the left subtree minus height of the right subtree should be less than or equal to 1. So here the condition failed. That is the reason the imbalance occurred at the node 3. When the imbalance occurred, what we are supposed to do? We need to balance it. So once we need to balance it, since the imbalance occurred the left side of the alpha, the case one will work. The insertion into the left subtree of left child of alpha. So the insertion, since one was inserted into the left subtree of left child of alpha. So left subtree of left child of alpha. So what is the left child of alpha? 2. Okay, the left child of alpha is 2. Since the 1 is inserted at the left subtree of left child of alpha, the alpha faced this imbalance. Once this alpha faced imbalance, we need to alter this particular imbalance situation into like this 2, 3. That is, you are since the imbalance occurred at 3 because of the insertion into the left subtree, you are supposed to perform the rotation operation on the left subtree, so of the alpha. So left child of alpha, on the left child of alpha, you need to perform the rotation operation. The rotation operation will be like this. It has to be rotated like this. Whenever rotation operation was done in such a way, then 2 will become the root node 2 will become the root node, and 1 will become the left child, and 3 will become the right child. So this is what the property. This is what the rotation operation that need to be performed. So when after rotation operation, if you look at height of left subtree is here. What is the left subtree height? 0, and right subtree height is 0. 0 minus 0 is 0, which is less than or equal to 1. So now the tree is balanced. It is just like since the imbalance occurred due to the left subtree, you take this 2, that means you hold this 2 and pull it up. Whenever you pull it up, automatically the 3 will fall at the right side and 1 will fall at the left side. So this is the way you are supposed to do this particular rotation operation. So after this, to easily understand, the next case is an insertion. We will consider the case 4, which is exactly opposite of this. The case 4 is like this: an insertion into the right subtree of right child of alpha. So what is the right subtree of right child of alpha? Here, assume that 5 is the node which is inserted into the binary search tree. The insertion will be taken place at the right subtree of right child of alpha. So assume that this is the 3 is the alpha now. Since the 5 is added to this binary search tree, then this was added to the right subtree of 3 and into the right child. So because of this, the imbalance occurred at the node 3, because the height of the left subtree is 0, but height of the right subtree is 2. 0 minus 2 is 2. The height balancing condition was not satisfied. So the reason imbalance occurred here at node level 3. So now what you are supposed to do, since it was occurred, the height balance occurred because of the insertion into the right subtree of right child of alpha. So you need to catch hold of the right subtree and pull it up. So whenever you pull it up, then 4 will become the root, and since you are pulling the 4 up, so the 3 will fall at the left side and 5 will fall at the right side. So this is what the rotation operation that you are supposed to do. So this case 1 and case 4 are a kind of mirror images, where in case of case 2, is the insertion into the right subtree of left child of alpha. So for example, K3 is a key 3. Since K2 is added, is included into this tree, which is at the right subtree of left child of alpha. Here alpha is K3. So because of this reason, the imbalance was occurred, because K3's left subtree's height is 2 and right subtree's height is 0. So 2 minus 0 is 2, which is violating the property of the height balancing. So that is the reason what you are supposed to do is you need to perform the rotation operation on the alpha's left node. So on the alpha's left node, you are supposed to perform the rotation operation. How you are supposed to perform the rotation operation? You need to push the K1 down and K2 must be linked to the K3 left. So this is what is called left rotation. You need to perform the left rotation. That means here K2 must be brought to the left of K3 and K1 will be pulled down. So this K2 and K1. So once you do it, this particular left rotation operation on K3's left, then it will become like this: K3, K2, K1. Once this is done, it will look like case 1. So once it is done like this, it will look like case 1. Now catch hold of K2 and pull it up. Once you catch hold of K2 and pull it up, then K1 will fall at the left side and K3 will fall at the right side. Now you look at the balancing factor. Then K2 balancing is height of the left subtree is 0 minus height of the right subtree is 0, and 0 minus 0 is 0, which satisfies the height balancing condition. This is called left rotation, and then performing the pulling up operation. So this is what is called left rotation. So you need to perform the left rotation on the alpha's left. Then you need to perform the right rotation on the alpha's right. alpha's left. So alpha's left, see, for example, here K3 is equal to alpha. So here K3 is left. On K3 is left, you have performed the left rotation. So it becomes like this. On K3 is left, again perform the right rotation. Then the right rotation means here this will be performed. This rotation will be performed like this. This rotation will be performed in such a way so that K2 will come up and K3 will be at the right side and K1 will be at the left side. In the same way, case 3, the insertion into the left subtree of right child of alpha. The insertion into the left subtree. So here K2 is inserted the left subtree of right child of alpha. Actually, this is the mirror image of case 2. Here case 2, this is the shape you got, like a like a less than shape, and because this is the mirror image that you will find in the case 3, which you find here greater than shape here. So K1, K3, K2, since the imbalance occurred at the K1 because of the insertion of K2 into the left subtree of right child of K1. So for this, what you are supposed to do is you need to perform the right rotation. You are supposed to perform the right rotation on K1's right. So if you perform the right rotation, then K2 will come here, K3 will go down. So K2 will come up and K3 will be pushed down. So whenever K3 has came up and K2 has come down. Sorry, here K2 has to come down. Actually, this is the wrong way I have written here. Actually, here you are supposed to get here perform the right rotation on K1's right. Perform the right rotation on K1's right. So if you perform the right rotation, then K2 has to come up. So K2 has to come up and K3 has to push it down. Once you get this, then it will be like a case 2. So 3, 4, 5. Once you got the 3, 4, 5, what will happen? Here you are supposed to pull it up. Whenever when you pull it up, then this will become uh, here this will become K2 and this will become K3 and here it is K1. So K1, K2, K3. Okay. So K1, K2, K3 and now here you will get, since K2 is in the middle, you have to catch hold of K2 and pull up. So when you pull it up, then it is K2 and here it is K1 and here it is K3. So these are the rotation operations that are supposed to be performed to make the height balance. Now, so far we have seen are simple nodes. There may have some child nodes also. That means 3 may have some child node and it may be having right subtree and maybe right subtree may be having children. In such a cases, how this particular rotation operations will be performed. Now, here case 1 and case 4, where you are supposed to perform the single rotations. Where in case of case 2 and case 3, you are supposed to perform the double rotations. Because first you need to adjust the right subtree or left subtree is left child. Then you need to perform the single rotation operation, thereby it will become the double rotation. So here single rotation operation, case 1 and case 4 will be done like this. Rotate with left child. Now K2, K1 was there and X is the child of K1 and Y is the right child of K1 and here Z is a node which is the right subtree or right child of K2. Now, if you look at the height of left subtree is like this. It is 2, and the right subtree is 1. So 2 minus 1 balancing was happened. Now, assume that there may be a node called K3 above K2. In such a cases, K3 is facing the we may face imbalance because the height of the left subtree is 3 and right subtree is 0. So in such cases, you need to perform some rotation operation on the this particular left subtree of or left child of K3. In such cases, what you are supposed to do? When you pull the K1 up, what will happen? This Y link will slide and will touch the K2. Okay, this it is just like assume that there is a key ring, and in the key ring you have 3 4 keys. Okay, you catch hold of one key and pull it up. Automatically, it will fall. The remaining keys will fall either the left side or right side. So the same concept you realize in case of these rotations. So for that, you look at here. When K2, K1 and some X is there, directly you have taken the K1, you have catched hold of the K1 and pulled it up. Okay. But if K1 is having the right child, then what to do? This right child must be attached to the K2's left, and K1 must be pulled up. So once the K1 is pulled up, this Y will go and touch the K2's left, or it will be arranged, it will be fixed to the, or it will be assigned to the K2's left. So now the Y will become the K2's left, and Z is the K2's right, is as it is like this, and X is left of K1, it is as it is like this. So this is the arrangement will be happening. So this is the arrangement will be happening. For example, this is the tree that we are going to construct. This is the tree that we are going to construct. By adding 6 into the tree is imbalanced. By adding the 6 into the tree is imbalanced. The reason is, if assume that there is no 6 here, now the height of the 5 root node is the height of the left subtree. What the height of the left subtree? 1 2 3 3, and height of the right subtree 8 and 7 2. 3 minus 2 is 1. So height is balanced perfectly here. But if I insert the element 6 into the tree, now here the height of the left subtree and height of the right subtree. Now still it is balanced at the root, but the imbalance was occurred at the node 8, because 8's right subtree is the 8's left subtree height is 2, but right subtree height is 0. 2 minus 0 is 2. So thereby height balance factor was disturbed. So the height balance or height imbalance was occurred at the node 8. So whenever this height imbalance was occurred, because of the insertion of the element into the left subtree of left child of alpha, which will fall under the case 1. So in such a cases, what you are supposed to do? You are supposed to take the 7 and perform the rotation operation. So what you are supposed to do? You are supposed to perform the rotation operation with the left child of 8. So rotate with the left child of 8. Perform the rotation. Then what will happen? 7 will come to the top. So 7 will come to the top, and 7 will become the right child of 5. 7 will become the right child of 5, and 7's left child will become 6, and right child becomes 8. That means here you are supposed to perform a right rotation on the left child of 8. So whenever you perform the right rotation like this, then 7 will come up and 8 will go down, push it down, so that it will be like this. Now you check the height of the 7. Height of the 7 is balanced. Height of the 5 is also balanced, and height of 2 is also balanced. Height of 4 is also balanced. So thereby entire tree will become balanced. So please remember, the balancing factor is not only at the root, but for every node the same balancing factor must be must be satisfied. That is height of left subtree of every node and minus height of the right subtree of every node must be less than or equal to 1. Now we'll go for the operation of rotating with right child. So previously we have gone for rotating with the left child. Now this is case 4, that is rotating with the right child. What is the case 4? This is the case 4. So case 4 is the mirror image of case 1. Okay, case 4 is the mirror image of case 1. So case 4 in which the rotation operation. So simple rotation operation here, K1, K2 and K2 is having the left child as Y and right child as Z. Now imbalance was occurred at K1. Now what you are supposed to do? You are supposed to perform the rotation operation on the K2. So what is the rotation operation you are supposed to do? Catch hold of K2 and pull it up. So once you pull it up, what will happen? The Y will slide and will touch the right of K1. Okay, Y will slide and will touch the right of K1 and K2's right will become Z. That means you are supposed to uh, attach the alpha's right left child to the alpha. Okay, and K2's left must be alpha and K2's right is as this. This operation you are supposed to perform. So catch hold of K2 and pull it up. So thereby K1. So left of K2 will be attached to the K1's right. Left of K2 is what Y. This is attached to the K1's right. Now we'll take an example, simple example. Let this is a tree. So far the height is balanced till you insert the node 5. By adding 5 into the tree, the height is imbalanced. So it resembles the case 2. It resembles the case 4. Actually, this is case 4. It's not case 2. This is case 4 because the height imbalance was occurred because of the insertion of the node into the right subtree of right child of alpha. So catch hold of 4 and pull it up. 4 will become the right of 2 and 3 will fall at the left of 4 and 5 will be at the right of 4. So next we will insert 6 into the tree. Currently the tree is balanced because height of left subtree is 1, height of right subtree is 2, 1 minus 2 is 1. So the tree is balanced at present. Now next we will insert 6 into the tree. So 6 will be compared with 2. So 6 is greater than 2. So it will be moved to the right side. Now 6 is compared with 4. 6 is greater than 4. Now it will be moved at right side. 6 is compared with 5. 6 is greater than 5. So it will be placed at the right side of 5. Whenever it is placed at the right side of 5, the imbalancing was occurred. The imbalancing was occurred at the root because root's left side is 1, the height is 1 of the left subtree is 1 and but the right subtree is 3. Height of the right subtree is 3. 1 minus 3 is 2, which is violating the height balancing property. Now what you are supposed to do? You need to perform the rotation on the alpha's right. So what is the alpha's right? Here 4. So once you perform the rotation operation on the 4, then 4 must be pulled up. When you pull the 4 up, then 3 will become the right of 2, 3 will become the right of 2 and 4 will be pulled up and 5, 6. Now, so the tree is imbalanced, so perform the rotate with the right of node 2. So rotate with the right, so perform the rotation operation. Then the 4 will come up and 2 will become that is the root will become the left of node 4 and 5, 6 are the right of 4. You look at after performing the rotation operation, it should not violate the binary substitutive property. What is the binary substitutive property? the elements at the left subtree, all the elements at the left subtree must be lower than the root. Elements on the right subtree of a root must be greater than the root value. So this is what the binary search tree property. You look at in any of the rotation operation, this particular condition, binary search tree condition is satisfied. You look at 5, here 1, 2, 3, 4 are the elements are less than 5, and 7, 6 and 8 are greater than 5. So for every node in the tree, the binary search tree property is satisfied. This is what the binary search tree property with height adjustment. That is what is called AVL tree. Now let us see the case 1. In this rotate with left child. Rotate with left child. In this rotation with the left child, the first one is you have to consider a temporary node. This particular code was written in C++. Many requests are coming from some students that the code can also be explained in C++. So anyhow, I have written this notes in C++, and I am going to give you make another video on coding the AVL tree in C programming. That I will do it shortly. So you can view that AVL tree operations using C programming, and this code what I have written in the notes is in C++. The one who are comfortable in C++ can use this code, or they may use the code that I have made in the another video, the next video, that is inserting the elements into the AVL tree using C programming. Here I have used templates concept. The templates concept means templates are the generic classes where where with one declaration you can instantiate with multiple data types. So this is what the genericity or templates in C++. Here the template will be like this: void rotate left child AVL node star ampersand k2, which is the address of k2, and constant. There should not be any change, should not be modified. So that is the reason I have mentioned constant. AVL node is just like struct node star k1 in case of C programming. In temporary pointer, you are supposed to place the k2's left. So here the imbalance was occurred at the 3. So what you are supposed to do is you are supposed to place the 2 1. This is k2's left. K2's left is there. Whatever the k2 left is there, or we can say here in case of k2, what is the k2 left is there. This k1 x y, this entire subtree will be kept in the one temporary variable. Okay, this will be kept in one temporary variable. What is that? Star k1. That is called star k1 here in temporary variable. Now k2's left is equal to k1 right. So k2's left, now k2's left is equal to k1's right. So for k2, I am going to attach the left child as y as the left child to k2. Okay, y as the left child to k2. Now this is complete. K2 y z is completed. Now what you are supposed to do? For k1's right, you need to attach the k2. So for k1's right, you need to attach the k2. Thereby what will happen? K1 x. This is as it is like this. Now k1's right already you have attached to the k2's left. So k2's left, then this arrangement will be happen. That is just like pulling the k1 up. That means this right should be attached to k2. Before that, you are supposed to keep this subtree, left subtree, into some temporary pointer. Then you are supposed to perform this particular assignments. So temporary node star k1 is equal to k2 left. K2 left is equal to k1 right. Now k1 right is equal to k2. This arrangement you are supposed to do. After making this arrangement, you need to check the height balance. That means height must be balanced, or height must be calculated for every node and should be saved. K2 height is equal to maximum of height of K2 left, comma, height of K2 right. This you have seen in the binary search tree also. Whatever the maximum of left subtree, height of the left subtree and height of the right subtree to be taken plus 1. That is the K2's height. K1 height is equal to maximum of height of K1 left, comma, K2 height. Whatever the K2 height, because K2 is added at the right side, K2 is added at the right side. So already K2's height is calculated. You just to take the K2's height and the left subtree height. Okay. Whatever is the maximum, that you take it plus 1. Thereby it will become the K1's height. So K2 is equal to K1. So since we have rotated, so we should have the control of the root. So the reason K2 is equal to K1. This is the step you are supposed to do for the left rotation, or rotate with the left child. In the example 3, 2, 1, okay, this is the case 1 example we have seen previously. Let K2 is equal to node 3. So K2 is equal to node 3. AVL star K1 is equal to node 3 left. What is the node 3 left? Which is 2, node 2. Okay, which is node 2. Node 3 left is equal to node 2 right. Node 3 left is equal to node 2 right. So node 2 right is null, so nothing to be added. Node 2 right is equal to node 3. So what will happen? It will become 2, 1 and 3. Right? Now node 3 height. What is the node 3 height? Is equal to maximum of height of node 3 left. What is the height of node 3 left? Which is minus 1. Initially minus 1 will be there. Okay, comma, height of node 3 right. Whatever is the node 3 right height, which is also minus 1, because left subtree is 0, left subtree is null and right subtree is null. When tree is equal to null, return minus 1, else return 0. So this is what the height function will define. So minus 1 minus minus 1, which is minus 1 plus 1 is equal to 0. So now the height of 3 is 0. Okay, height of 3 is 0. Now node 2 height is equal to maximum of height of node 2 left. What is the node 2 left height? Is 0, because 1 is the leaf node, comma, height of node 3. What is the height of node 3? Which is which is 0. So what is the 0? Maximum of 0, comma 0? 0 only. So 0 plus 1. So that is 1. So node 2 height is currently 1, and node 3 height is 0. So 2 height is 1 and 1 height is 0 and 3 height is 0. So nowhere the height imbalance was occurred. So that means after rotation, whatever the resultant value you got, or whatever the resultant tree you got, is balanced. So AVL node consists of 4 fields. So that are, one is data, because data is the element that need to be stored in the node, and second one is the height, because we need to take care of the height of each and every node, and address of the left child and address of the right child. So that is the reason the structure will be formed like this: template, class T, class AVL node, T data, AVL node star right, left, AVL node star right, integer height, and this is the constructor, and friend class is AVL tree. This is in C++. But in case of C programming, struct AVL node, okay, int data, struct AVL node star left, struct AVL node star right, int height. So this is the simple representation of the structure. Where if you want to write it in the template, you are supposed to write in this template form. So in the next lecture, we will see the case 2, case 3 and case 4 operations, and also along with this one, we will see the deletion operation from the AVL tree.